Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I'm super happy to have Rosalba Perna with us today. Hi, Rosalba.
Hi, nice to see you, and thank you very much for the invitation, by the way.
Well, thank you so much for writing such a lovely article that I picked it that we could talk about it. So it's all absolutely wonderful. Rosalba, where are you at?
I am in Stony Brook, my office first day since 6 months, so it's been nice to see that the plants are still alive. One of my colleagues have been alternating around giving water.
What kind of plants are they?
It's like one of this yucca type, which has a very long life. I can see.
Yeah, apparently without water.
They can stand a lot. I have experience now.
Yeah, that's great. Yeah, we have a few plants in Arizona here, like cactuses that don't need a whole lot.
Yeah, those are great for offices, especially during COVID times.
Yeah, gosh, I haven't been in my office in since March 2020 was the last time I was in my office. So obviously are you planning on is Stony Brook planning on being in person in the fall?
So Stony Brook is planning on being in person. That's hopefully that will stay the case because, as you know, with all these variants now. So we were supposed to be also mask free up to like a few weeks ago, and then plans changed as now. So we'll be required to wear masks indoor, and but you know they're also requiring vaccinations or regular testing. So hopefully that will help. Yeah, it's a good thing. So we'll hopefully we'll help to keep cases down and having it normal as normal.
Fingers. Yeah, we're
the new normal.
Yeah, the new normal. Yeah, we're scheduled to go in person as well. Starting actually, I start teaching next week, August 17th.
Oh, wow. Okay.
But I'm teaching online, so it doesn't totally matter. It's good. I think that is a really awesome chalkboard after you're right there. I see all lovely theoretical scribbles. I noticed.
It is actually it's a more of a historical one because now, especially with the but it is like a collection of things from like some former student, former postdoc, right into corner, and then like I like, okay, if I really I like to keep it because it's like more memory because now I do everything, more it's online, and so it's a more of a
it's a forever board. It just lasts forever.
Board.
So that's really cool. Very nice. Cool. So speaking of scribbles, Rosalba, what do you like to do for research?
So I am a theoretical astrophysicist, kind of rather broad, and I've had throughout the my time, since my PhD, variety of research interest, which started from gamma ray burst. That was my thesis on, but also gravitational lensing. Actually, the first part of my thesis was on gravitational lensing, so completely uncorrelated. And then I went through a period of a lot of interest in neutron stars and magnetars. And then more lately, I've also had interest in exoplanets, both in planetary atmospheres, but also N-body. I have a fantastic graduate student who actually has a super fast code for N-body dynamics. So also advertising him since it will be on the job market. And so a lot of different interests. But compact objects, I had to say, throughout, they've always been fascinated to me, and in particular neutron stars and black holes. Which happened to be part of this the paper that we are discussing. So compact objects always have a special place in my heart, even though every so often I go more low energy or more mundane, with the planets.
Very cool, very cool. And that is going to bring us to this very lovely APJ article. Accretion-induced collapse of neutron stars in the disks of active galactic nuclei. And Rosalba, take us away.
All right. So thank you. So I will start by talking a little bit of how I came onto this topic, because it sort of also puts it into a broader context. So for me, as I said, I work on a lot of different topics, but AGN disk was a topic of which I never touched upon. And the way AGN disks were in my mind, they are, the disks like Shakur disks, they're just gas. So they're feeding the supermassive black hole, and they are responsible for the luminosity that we see in AGNs. So that were AGN disks for me. And then it happened at a conference where we were like people were put in groups after, so kind of almost random, random association. And I was actually in a talking group with Savi Ford and Barry McKernan, who are AGN experts. So we tried to find something to talk about. And I was, more the GRB person, so more familiar with the GRBs.
Mm-hmm.
And so something that they show me as we were talking about AGN and disks, they're like, there is like a lot of variability in AGNs that we do not understand. So there are some light curves that rise and decline, and they cannot quite be explained with just blobs of material. So they were showing me some of this light curves, and I was like, this sounds interesting. One of that looked to me like it could be an afterglow, like an orphan afterglow of a GRB. So I was like, wait a minute. So are there stars in energy and this? And I'm like, of course there are stars there. There are compact objects. So from there, the next person I talked to was Matteo Cantiello, and I told Matteo, how about stars in AGNs? And Matteo was actually working on a paper, which I realized as I looked on the YouTube channel,
yes,
has been indeed features. So at the time he was working on that. And he said, yes, there are stars and actually evolving in a very interesting way. And as a matter of fact, from that conversation, so they were not looking in their previous paper, they were not considering angular momentum. So as I was interested in gamma burst, we talked about looking also at a rotation that led to another paper where Adam Jeremy is the lead author, which is you may be the editor also of the paper, and that was published in the APJ just before, like the volume just before this volume here. So I started all of a sudden to think about stars and their death in AGN disks, and as I was thinking more about this topic, I realized that there was a literature that I'd been not followed as closely related to LIGO observations, and the fact that there have been black holes with masses that are not easily explained by standard stellar evolution. And these are the black holes in a lower mass gap where, between 2.5 and 5, it's sort of unclear whether there should be some theories and maybe not other. It's an unclear. It's a range that has not been populated in the past, and there have been some ideas as to why it should not be populated. And then there is the apparent stability gap, which actually much more strongly forbidden by stellar evolution. However, as you know, there have been black holes detected in both gaps, and by LIGO, and therefore and therefore, like AGN, that's a place where AGNs came as a possible explanation. Why AGN disks? Because in an AGN, there's multiple ways to form black holes of larger mass. So number one is through hierarchical mergers, because in the disk of AGNs, black holes in general, compact objects merge more easily. And therefore, one can have subsequent generations of black holes, which lead to bigger black holes. And second, because black holes themselves can accrete very rapidly. And this is something that will be very related to the topic of the paper. So the fact that AGN disks have very, very high densities that makes them to be very special environment in the way they alter the evolution of compact objects. So for black holes, it's just a matter of increasing mass and growing, but they're still black holes. However, for stars, as Matteo and collaborators showed, their evolution can lead to very special behaviors. And for neutron star is something that we consider in this paper. So this provides a little bit of the broader context of how this came about as far as the general motivation, for it. So let's now talk a little bit more about the paper itself, and also I want to acknowledge my collaborator. So a fun, fun facts that one likes to say, because the first person I talked to was actually Zoltan Hyman, as we were both runners, and we came across one another on a run. It was going south from Columbia, I was going north from Lower Manhattan. And then we decided, okay, how about we run together? And then there was the period where I just started to think about that. So I started to talk about Zoltan with Zoltan. And actually a lot of the early ideas were discussed while doing long runs.
Very cool.
So there was a very fun starting, and also how a lot of the paper and the main ideas were being discussed. Ian Murray was also helped a lot with the general ideas, and Hiromichi, as we'll see later, he was actually key in producing the calculation of the rates. He had already code that was set up for computing the rates that we'll be talking about of accretion-induced collapses. So this is with very much knowledge in the role of the collaborators and the fun runs with Zoltan.
I wish you many more happy runs.
Thank you.
Every time you run, you put out an article. So
we were after we finished this paper on the following run with Zoltan was like, okay, so now we have to discuss the next project, which actually we have already.
As a produces an article. That's awesome.
It's been a fun. So let's going a little bit more in the specifics of this. So this is again like a little bit more of background. So I already mentioned there are stars in AGN disks, but for all of you were like, I was not familiar with how stars end up in the disk. So there are fundamentally two ways by which stars can be found in AGN disks. So one is by in situ formation. This is basically the disk that fragments, and then it says like standard, standard quote unquote formation of stars. And this is again, it's not in the paper. This is just background as to how stars end up in AGN disk. So one is in situ, and the other is via capture. There is a cluster of stars very close in the inner few parsec of AGN and its disk, like 10 to the 7 or so for typical AGN. And as these stars move around, when they cross the disk, they will lose momentum and energy, and a number of them will get captured. So this is how a lot of stars end up in the disk. And so also compact objects, because there are a lot of stars that die in the disk, and then similar to stars, also neutron stars and black holes, but here we care about neutron stars, end up in the disk. So there will be a large number of neutron stars. So this is the starting point of everything. So now let's see what is so special about AGN disks, why a neutron star in an AGN disk has a different life. So the reason is that AGN disks have extremely high densities. And just to give, order of magnitude estimates, it's something over 10 to the 10, 10 to 20 grams per centimeter cube, which may not, as a number by itself, may not say much. However, if one takes just, Bondi standard accretion, you translate it, so in accretion rate, that gives accretion rates on the neutron star on the order 10 to 16, 10 to the 26 gram per second. So taking a face value. Just as a reference, the Eddington luminosity of a neutron star is 10 to the 18. So basically the bottom line is that for the largest majority of a disk, a neutron star will be accreting at Eddington rate. It cannot be much super Eddington for being a neutron star, but basically unlike it, so this is very, very different than the interstellar medium where they will accrete, they will accrete to mass over their lifetime, but will be a tiny bit, so they will not change their life as just being neutron stars. So this is like, it was a very interesting, like a very, like a sudden observations that yes, neutron star actually will undergo a phenomenon, which is this famously known accretion-induced collapse of a neutron star, which was turned into a black hole. And just to give you an idea of the time scale, so if one takes a neutron star, let's say 1.3 solar masses to star, which is what we consider in this paper, and it accretes at Eddington rate, it will reach, say, 2.2 as a rough whatever upper limit, in something like 30 million years.
Short.
30 times 10 to the 6th, 30 million years. So this is something which is comparable or smaller than the lifetime of an AGN disk. So basically, bottom line is that there will be a lot of neutron stars that accreting at the Eddington rate will undergo in a collapse to black holes. So this is a very simple fact. It's simply just accretion in the AGN disk. So it's a very simple observation. So all of a sudden we have an astrophysical setting where this phenomenon can happen. So the phenomenon itself, now we can go and maybe describe it in section 2. So the phenomenon of the accretion-induced collapse of a neutron star into a black hole is something that people had been studying and discussed a lot. From a physical point of view, it's a very interesting problem as a GR-MHD GR-MHD problem. So and there is a lot of history there, but without going through all of it, like for GR-MHD simulation, have generally been finding that when a neutron star collapses onto a black hole, it won't leave any mass outside the horizon. So this is a sort of key element. It's a very important element because if the neutron star leaves some mass outside of it, then mass is available for accretion at a later time. So basically, in vacuum, a neutron star collapsing into a black hole does not leave any mass around, so there will be no energy available from accretion. And I should say, just to be more precise, that these simulations are to be more complete rather than precise. This GR-MHD simulation have not explored all range of equational state of neutrons. So one thing that should be mentioned, just for completeness, regarding these solutions in vacuum is that they've been limited to specific equational states, and therefore they don't, they have not fully explored the issue. There have been more recently some analytical calculations or semi-analytical calculation trying to examine the possibility that there may be other, other equational states which would allow to leave some matter outside when the neutron star collapses. However, even if that is the case, it seems that the amount of mass that will be left behind is very small. So to zeroth order, we can assume that when a neutron star collapses to a black hole in vacuum, so if there is no mass, basically there is no power available from accretion for the black hole.
Okay.
So this is like result of a number of simulations. However, years ago, I had a very good postdoc, Bruno Giacomazzo, who is specialized in GR-MHD simulations. It was actually the one implementing the magnetic field in the Whiskey code. And so with Bruno, we actually decided to revisit the problem, but considering a neutron star, which is collapsing, but it has some mass around it, and we consider an amount of 0.1 solar masses as a typical number.
Okay. So
what was the result there was that as the neutron star collapses and the space-time dynamics, the space-time changes to arrange into the one for a black hole, it faced a very rapid accretion onto the black hole results. And the accretion rates were 0.02, 10 to minus 2 or so solar masses per second, which are typical of a short GRBs. So we basically argued that if a neutron star undergoes an accretion-induced collapse onto a black hole with some matter surrounding it, it will behave, will actually be very interesting as a phenomenon. So however, this paper was more than 10 years ago. But the point is that up to thinking about AGN disks, this remained more as just a purely, physical study, so to speak, numerical physical, because there wasn't really any, any context in which a neutron star would be thought to collapse by having a lot of matter around it. And then here we go with the AGN disks. We realize that this is actually a situation that can very easily happen. A neutron star in a typical location in the disk where we found which we found from the simulations here will will be subject to a flow of like something of 10 to the 3 solar masses. This is like, it's a huge amount of mass. Obviously, the neutron star won't accrete it all, will mostly be going in an outflow. But even if a tiny amount of that is retained by the neutron star, which is quite plausible, one will have a phenomenon like the one that in the paper with Bruno had studied in an astrophysical context. Cool. So here is the first type of transient, which is enabled by an AGN disk, and it is a neutron star collapsing onto a black hole and being surrounded by some mass, non-negligible amount of mass, giving rise to transient, which would resemble like a short GRB. This is number one. Yeah. Then there is, but there is not, not all to it. The second one is what happens when so this is independent now of the presence of matter or not. The neutron star, as it collapses, and this is again something that has been studied in and found in GRMHD simulations. So as the neutron star collapses, if the neutron star is magnetized, and most neutron stars, unless they're very, very old, they will have a magnetic field. So as the magnetosphere of the neutron star rearranges itself and reconnects, as the neutron star collapses onto a black hole, the black hole cannot have magnetic fields, as we know, for the Noether theorem. So this, former magnetic field energy will and magnetospheres around it will end up reconnecting. And as a result of it, this gives rise to pulses of electromagnetic energy. And this is where equations 1 and 2 are. So these are not. So these are from some simulation of Carlos Valenzuela, who did GRMHD simulation of the neutron star collapsing into a black hole, but specifically looking at what happens to the magnetosphere of the neutron star, how it arranges. And this is again one of several other simulations. So they all find very consistent results. So it's a very generic, might be slightly quantitatively varying, but basically there will be a strong pulse of energy. Now, where this energy will mostly go, it was argued this was looked at by Falk and Rezzolla with, at that time, it was a different motivation. And it was basically, one way to explain the famous fast radio burst. So this accretion-induced, basically the collapse of a neutron star onto a black hole, and the pulse of radiation that it's mostly in the radio, so the frequency is equation 3. So they would give rise to a pulse which is resembling a fast radio burst. Yeah. So that's very interesting. And again, in the paper, so Falk and Rezzolla, they proposed that the neutron star will have to collapse into a black hole, with some ways. The point here is that in AGN, this happens very naturally. So this is like what makes this very interesting. The fact that when you have a neutron star into an AGN disk, by its lifetime, most neutron stars will undergo this collapse. So there will be two, to summarize the first part, there will be two types of phenomena that can result. One, which is a short GRB-like, because again, it's not the standard short GRB, but resemble due to accretion of the accretion matter onto the black hole, and the other, which is purely of electromagnetic energy, which will resemble more an FRB type of event. And this can be both, can happen one after the other, because the magnetosphere arranges itself as the neutron star is collapsing onto the black hole, and then some, like a fraction of a second to a second later, they can be then if there was matter surrounding the neutron star, there will be the accretion onto the black hole, and this is the setup of a short GRB-like event. So this is like a phenomenology which is very cool, and would be it requires the conditions of an AGN disk again, because it requires a neutron star to undergo collapse and to be surrounded by some matter. So these are so this is the first part of the paper basically deals with what can happen in an AGN disk when a neutron star undergoes a collapse, and we relied on results from previous work as far as the phenomena that could happen. So the next question is, how often does that happen? So how do we go about it? And here Hiromichi Tagawa's code came very, very handy. So lots of credit to him for doing the right calculation. So Hiromichi is it's an n-body code that allows, basically standard n-body code that allows to calculate given a population of objects, how binary formations, binary disruption via 2-3 body interactions, and then once a binary is formed, how it evolves due to drag by the torques and drag by the gas in the disk, gravitational waves. And so forth. So all this, so it's a combination n-body plus semi-analytical prescription to following evolution of a binary. But basically, the bottom line is that with this code, it allowed us to calculate it for a specific case. So we called our fiducia model, like our typical AGN, which here says that we study one case in very much detail, which is an AGN of of a supermassive black hole of 4 times 10 to the 6 solar masses, sort of, semi-generic, sort of generic, typical. And then going to figure 1. So that has, which is somewhere later. So this is, it's discussed how the model works. So figure 1 has some of the results. So there are, so first of all, top and the bottom. And so first of all, the top has this IC. So these are it's the terminology that we used in the paper for, so isolated neutron stars that undergo in accretion-induced collapse. In the bottom panel, so I haven't said it yet, but I'll mention it now. So we also, in the paper, we also tracked how many neutron stars undergo a standard merger.
Yeah, okay.
Why is that interesting? Because a fraction of neutron stars that merge will leave behind, instead of a black hole, will leave behind a stable neutron star. Now, the fraction is equation state dependent, so that's, I mean, that's interesting in a way for its own right, because it's, it can give some information on the equation state. But basically, the bottom line is that for a range of equation state, one expects some fraction of neutrons of these mergers to leave behind a very massive neutron star. Now, those are particularly interesting because if they are, I mean, if they are produced by the merger to neutron star, they are very likely to be very close to the maximum mass. Probably it would just below, so I mean, you have 2 neutron star, you make you're stable, but probably it still be, it will be very massive. So basically, those are events that within a very short time will accrete, events like massive neutron star within a very short time will accrete, and then almost instantaneously will give rise to an IC. So those are also very interesting. So that's why we also kept track of those, because when a merger happens that leaves behind a stable massive neutron star, that will, on a very short time, that will yield another IC. So top and bottom are that's the two. One is the single isolated neutron star. The other are the ones that are basically mergers and shortly become accretion-induced collapse for them as well. So what this calculation yielded was also where this merger occurs, and as I will discuss a little bit later, this is actually very important information because different regions in the disks have very different properties, both in density and in temperature. So the density has a very steep power law. The temperature also is very different. Yeah. So for the observability, where exactly that happens, that plays a very important role. So what we found is that for this fiducial model, again with 4 times 10 to the 6 supermassive black hole, the most of the isolated neutron star in accretion-induced collapse happen around 1 parsec. This is basically a region where migrations tend to be slower, so that's why they tend to, accumulate in this area. And on the other hand, below 0.1 parsec, migration tends to be faster, and then binaries that end up in there, and then they end up migrating very quickly to very short distances, and that happens. That's the peak in the bottom distribution. So those are the reasons. Basically, migration plays a role in where these objects end up mostly populating. So those are the left panels. It's basically the location within the disk that's on the x-axis. The middle panel, on the other hand, that shows the height distribution. So why did we care about that? And this is again in light of how likely it will be to see a certain event. It's very important whether they happen very much in the disk, in the midplane, or whether there is some height. So as we can see, the ones from isolated neutron stars tend to happen more in basically the greatest majority at which are around well, they're 1 parsec, but so they tend to basically they happen more in the middle plane. So basically, by the greatest majority is below 1 scale height. So they will be very embedded. On the other hand, for mergers, there will be some fraction which are a little bit higher in the disk. So that will come back later when we talk about observability. And then on the right, the different colors are also subdivided, as I discussed early on, that stars, but also neutron stars, they can either be formed in situ, so stars that were they evolved in the disk, and others that were captured. So those are the two basically the two separations, just to so those are the two lines because they come from different they have a different history. And then on the right, it's the number as a function of time, because it takes as the code follows the accretion over time of each neutron star. So there is a time for the build up. That's why they start suddenly. And then after about 30 mega years, then you have more and more that they undergo IC accretion-induced collapse. The dashed lines, it's just a line showing 10 to the 8 year, which is a typical lifetime of an AGN disk. So it's just to guide the eye as to where what is a typical lifetime. So depending on if a disk is more massive and will live longer, one will have more of these events or not. So it basically relates to the lifetime of the disk. But it's important to to keep in mind that this what this figure shows, that it takes time for the for neutron star to grow to even assuming Eddington accretion. If actually we go to figure 2, we consider some so that's a little bit figure 2. It's like maybe the following page. So figure 2, we're basically considering also some variation on the model, just varying 1 parameter of the every time 1 parameter. But basically so neutron stars could, in principle, they've been seen. Let's say more could in principle. They've been seen to be able to accrete a bit above Eddington. This is some of the famously ULX, which turn out to be accreting neutron stars. So if say if neutron stars accrete 10 times the value of Eddington, then one will find that it takes, instead of 30 years for a neutron star to induce to have an IC, will be 3 million years, and therefore there will be many more. So basically, that's so there are uncertainty should be more than certain. There are variable, I should say, in the model. So these are also varying different parameters of the fiducial model, like velocity dispersion, the distribution density profile, or the size of the cluster of stars, or the size of the AGN disk. So So we didn't do systematic because the range of parameters is enormous. So we studied very much in detail one case and then say, okay, if we vary this or we vary that, how? So the numbers in the parentheses above show how the rates would vary if one of those parameters is changed. So then, given the rates per AGN disks, one can weight by so using the fiducial model, weighing by by a distribution, a cosmological distribution of AGNs to infer a global rate. So this is something that we also did. And the global rate, which is somewhere in one of the equations later, global event rates, right? Yeah. So
before we get there, let me ask, me make one or two comments, I guess.
Yeah.
It looks like the only ones that really shift the peak toward much closer to the supermassive black hole is this one Eddington, right? Because you get a peak here at 10 to the minus 3 on the scale height, and you get a peak here. So most of them keep that peak out at log R at about 0.
0, yeah.
A couple that really move it inland.
Yeah.
And the other observation is most of these are neutron star mergers, either in situ or otherwise. The number of the relative number of AICs, the blue curves, is generally small, or in some of these.
That's right. Yeah. Indeed.
Okay.
So that's indeed the case.
Yeah, very good. Okay. So global rates and.
So yeah, global rates, I mean, they're done, the usual standard way to basically one weighs, number of supermassive black holes, with distribution. So it's a standard cosmological calculation. So you weigh basically how many you have in a certain galaxy of a certain mass by how many galaxies you have IGN of a certain mass to calculate the global rate. So the numbers are, it's equation 6. So that's, there are a lot, I should say, there are a lot of uncertainties, obviously, in these rates, because like the size, each one of those parameters that I discussed before can influence. So this is done for one specific case. But basically, just as a general so the number, I think maybe they're quoted 0.07, 20 gigaparsec minus 3 just before equation 7. So the rates are somewhat smaller than they're smaller than compared to the ones that one has for long GRBs. They're also rather smaller than compared to the rates, the LIGO rates of binary neutron star mergers, which would rise to short GRB. So in a way, it's not surprising that we don't see routinely, let's say, this type of events from AGN disks. So the rates are smaller, but they're not negligible. So the other question, the other point, which we went a length here in the paper, but it's something which we are will be exploring more in the future. It's how to recognize these events, because right now we are just looking how many happens in an AGN disk, and what this does. But then the question is, what does to the actual luminosity of the transit. So we have all sorts of range of luminosity with gamma rays. When you have a short GRB type of event, you have everything from gamma rays to radio longer wavelength, and then the FRB are pulses or radiation, which are subjects to dispersion measure and self-absorption. So the question is, what are the likelihood to detect these events given an AGN disk? So this is something that we addressed, and this is the last section of the paper on the observability. So we looked at somewhat in detail, although still, was a back of the envelope calculation for this fiducial model, where we had, we know exactly what is the runoff density and temperature with within the disk, and that for we know through our calculations where they are mostly concentrated, so we know what are the local conditions at those locations. Yep. So basically, in a nutshell, just summarizing this section, yep. For a GRB-like event, they would appear at around 1 parsec for this type of AGN, because we found the optical depth to Thomson scattering around those regions to be 0.4, so less than 1, but it's not very far from 1. It should be, so it's like a really borderline. On the other hand, FRB type of transients will have a very large dispersion measure. So those will be more likely will have a very large dispersion measure if the medium is ionized. So it also depends very much on the conditions of the medium. Right. At those locations. So in the outer parts of the disk, the medium is generally neutral, and that would be fine for an FRB. However, if there is a short GRB associated with it, or also even just the neutron star accreting will generate luminosity over time, and that may ionize the medium. Mm-hmm. So the situation is actually very complex, and this is we laid out a lot of ideas and issues that go on. The fact that there is basically feedback by these objects onto the AGN disk. And this may affect the observability itself. So basically, for FRBs, we expect to see more the ones that will appear that are associated from neutron star mergers that happen higher up in the disk. So if they're embedded in the disk and the medium is ionized, then the dispersion measure basically would just kill, would not allow observability. Right. On the other hand, if the neutron star, let's say, it's not ionizing the medium much, or it's ionizing directions different than where the radiation. So there's a lot of things that can go on. Then it would be observable also from the inner parts. So just to basically,
yes.
Yeah, I was going to basically just summarize this section, but also more a dual paper. So basically, we have a very interesting new phenomena associated with with this calculation, dispersion measure that basically I said in words that show that's very high, and for free absorptions. Yeah, so the estimates at the local conditions, the local. But basically, so we have a very interesting new phenomena. So this accretion-induced collapse of neutron star to black hole that we've never seen before directly. And where in AGN disk provides an environment in which these events very naturally happen. They're bound to happen because if you have a neutron star, they will accrete, accrete ad infinitum easily, since there is so much mass available, and then they will undergo collapses. So it's a very exciting fact that we can have these events. Now there's these events, whether or not surrounded by mass, are expected to give rise to transient. And the question now, and which is also in the future as we move forward, is to understand a little more how in detail, first of all, what fraction we actually expected to see for AGN different masses, but also to actually better simulate the light curves of these events. So if they are coming from a region which is which is absorbing, there won't be any more sharp peaks, let's say, from in X-ray gamma rays. So they will appear much more diffuse. They may be down scattered. So we want to basically understand how this will actually look like coming up from different regions of the disks, and eventually going to check against this. So it all goes back to the beginning. A lot of this variability in AGN light curves, which is unrecognized. Now with the LSST, we'll be detecting so many of these variable, these variable sources. So this will be actually, towards the future will be, and also there is a lot of, the FRB also being, that's the other side of looking with the radium.
Right.
So there is a lot of observational capability now. There will be looking for this type of events, also the more rare ones. So let's say, if these are a small fraction, it's possible that, coincidence with the AGN, they have not been seen yet. But also it's possible that they may have been seen, like that some of this unrecognized AGN variability, some of which looks like, that's how it all started for me. This looked like it could be like an afterglow. So they may already, been there. So it's a very exciting, like both from a theoretical point of view, because this generated now like a lot of, like, there are several projects that are basically now we're having follow up with this. Also, there have been, I should say, it's been nice to see that there have been other works actually, like, as some motivated by, like other phenomena in AGN disks, there have been other groups such as, looking at supernova in AGN disks. So this has triggered people thinking of, TDs in AGN disks. So thinking a lot of, a lot of all sorts of stuff that, so AGN disks went from just being, elements of gas accreting onto obliquals to being very fun places to host compact objects and giving rise to exciting events. So that's, I think that's
well, fun is good. Fun is always an important part.
Absolutely.
I'd say, the whole topic over, the last, at least the last year, I would say, of people submitting manuscripts is this whole area of stellar phenomena in AGN disk in a variety of fashions, and this being a good example of one that hasn't been considered. So it's really cool. I'm looking forward, over the next couple of years to some of the observations that will come out from LSST and CHIME and JWST. And also you mentioned you have a number of theoretical works, because right, a lot of this was idea, and so now take that next step and let's put it in context of that AGN disk. So very cool, very nice. I look forward to seeing some of your future articles.
Thank you very much. Thank you.
All right, Rosalba, I want to thank you once again very much for sharing your very thought-provoking article with us.
Thank you very much once again for inviting to talk about it.
Thank you, everyone, and I hope this made your astronomy day just a little bit better. Thank you, and we'll see you soon. Bye-bye.